13 from the reviewer, the problem set, or whatever that you want to talk about. I'm happy to take a couple of questions here to start. Yeah, Lucas.
Do one from the last set of problems.
Yeah, that like 50 whatever to whatevers.
Yeah.
Sure, 48 to 53, I think. Yeah, I'll grab one. I mean, that makes sense, doesn't it? Happy to do it.
46.
Well, he said the last block of problems. So one of these evens. 50 sounds great. All right. So the first thing I'm going to do is identify that I'm looking for 4 answers. Right? How do I know there's 4 answers? It's degree 4. Excellent. Then I'm going to use my rational roots theorem to figure out the possible rational solutions. So those are going to be the factors of the constant term divided by the factors of the leading coefficient. Now, since the leading coefficient is just 1, it's just going to be the factors of the constant term, right? Because anything divided by 1 is itself. So my factors of 64 are 1, 2, 4, 8, 16, 32, and 64. Now that I've done that, I'm going to look at the graph and figure out where to start, right? Which one of those from the list is going to be a good synthetic division candidate? So I'm just going to go ahead and type my equation into my calculator. So x to the 4th plus, is it plus or is it, it's plus, 12x squared minus 64. And then I'm just going to do that on kind of the standard window. So I'm just going to do zoom 6. And I'm looking at the x-intercepts. So I see an x-intercept here at -2, another one here at +2. And that's good because I see +2's on my list and -2's on my list, right? So both of those should be good candidates for synthetic division. So it doesn't matter which one I pick. I'm just going to start with one of them. I guess I'm going to start with the -2 because I wrote it down first. I do have to be careful, though, when I'm setting up this synthetic division, because if I look at the polynomial that I'm using, I go from degree 4 to degree 2. I skip the degree 3 term, so I need to make sure I put a 0 there. And then I went from degree 2 to degree 0. I skipped the degree 1 term. So again, I also have to make sure I put a 0 there. So there I'm all set up. So I'll just do my synthetic division. I'll bring the 1 down. -2 times 1 is -2. Add down. -2 times -2 is 4. Add down. -2 times 16 is -32. Add down. -32 times 2 is 0. That's what we're hoping to get. The problem is if I look at what's left, I have a constant x, x squared, x cubed. Do I know how to solve a cubic polynomial? And not by hand, right? So what am I going to do? Well, I'm going to just do another synthetic division using my other candidate. And that worked, which is great because the remainder now is quadratic, and I know how to solve every quadratic. So let's put this thing back together. I have a factor of x plus 2 from that piece. I have a factor of x minus 2 from that. And then I have x squared plus 16 from that. That's all equal to 0. Now that I've got it in a factored form equal to 0, I can set each piece equal to 0 individually and then solve. To solve x squared plus 16 equal to 0, I could use the quadratic formula, but since there's no linear term, there's no degree 1x, I can just solve this directly, which is going to be a heck of a lot easier. So I'll subtract 16 from both sides, square root both sides. Square rooting both sides gives me the plus or minus. I'm square rooting a negative, so I get an I, and the square root of 16 is 4. So that's solution 1, solution 2. 4i is solution 3, and negative 4i is solution 4. That's all 4 of them. I know I'm done. Does that feel okay? So the process here is a little bit lengthy, but nothing on it is absurdly difficult. Like symbolically or algebraically, the details aren't so bad. It's a lot of just like whole number arithmetics and understanding like, what do I do with the result is the hardest part. But the process is not too bad if you understand what's going on. Okay. You feel good, Lucas? Great. Anyone else want to do one? Okie dokie. That's cool with me. If it's I'm cool, if you're cool. Is everybody cool? Bunch of little Fonzies in here. That has no cultural reference for you, does it? Fonzie was a character on a show called Happy Days, which is like the most popular show in America for a long time.
I saw the dude in that.
Yeah, it's Henry Winkler.
I saw him like last week.
You saw him?
He was at Autorama.
Interesting. That's cool. Henry Winkler played the Fonz and he was like the coolest person in America for like 10 years. Anyways, he wore a leather jacket on the show. Right? I know. All right, let's talk about chapter 14 then. So ideally, these chapters we're doing here at the end of the semester would be review things from Algebra 2. I know that you have not done these things from Algebra 2. That's okay. We're going to go through and do this slowly and carefully as if you're seeing this for the first time because I know you are. Okay? Chapter 14, we're going to be talking about about rational functions. So we're going to start off by just defining what we mean by a rational function. So our definition for a rational function is just basically one polynomial divided by another polynomial. I write that as the rational function r of x is equal to p of x divided by q of x, where p and q are polynomials. Everybody feel okay with that? Just one polynomial divided by another polynomial. That's all we're talking about here. And it's nice because what have we just finished talking about? Polynomials, so that should be like the component pieces for the rational function should still be pretty fresh in our minds. Feel okay? So domain, let's talk about the domain for a polynomial or for a rational function. Now, a polynomial function just includes the operations of like addition, subtraction, multiplication, right? Everybody agree with that? And we know that if we have like real numbers, if we add, subtract, and multiply, it doesn't matter how we do it or the order we're doing it in, we're going to get a real numbered answer back, right? The domain for any polynomial is all real numbers because you can always plug any real number in and you'll never get anything undefined. But if we have a rational function, what other operation is included here? Other than just addition, subtraction, multiplication? Division, right? Because we have one polynomial divided by another polynomial. Where can we get in trouble doing division? Not exponents. Think back to like elementary school. When we divide by 0. Yeah, that's right. So, to find the domain, we're going to have all real numbers except for the x's when the denominator is equal to 0. Let's maybe... Okay. So let's do a couple of specific examples just to kind of hammer this idea home. So first thing I'd want to do is check to make sure that the function I'm looking at is a rational function. I have x plus 4 divided by 2x minus 1. Both of those polynomials? Definitely, right? They're just linear mx plus b's, definitely polynomials. So all I need to do is take the denominator and set it equal to 0 and figure out the x or value for x's that makes the denominator equal to 0. So we'll add 1 to both sides and divide by 2 and I get 1/2. So my domain then is all real numbers except for 1/2. Does that feel okay to everybody? It's pretty easy, right? But this is not the way we're going to write our domains, right? First semester, what did we use to write domains and ranges? We used interval notation, right? What did interval notation look like? Had like the brackets and the parentheses. So if we're talking about all real numbers except for 1/2, where do we start our domain at? It's the smallest number that we can have. Well, -infinity, right? And we conclude all the numbers from -infinity up to what value? No, because we have a gap. We have a little hole in our domain at what number?
0.
Not 0. 1/2, right? That's the value for x that doesn't work. And we'll use a parenthesis on the 1/2 to indicate that the 1/2 is not included, right? That's what the parenthesis means. What did the bracket mean? That it would be included, right? But we don't want to include negative or include a half because we know that it's not in our domain. And we do the union symbol. And then where does our domain pick up at? Well, 1/2 to positive infinity, Does that feel okay to everybody? Not a big deal, right? Let's do one more example. Before we start transitioning forward. Let's say we want to find the domain for 3 minus x over x cubed minus 4x. First, let's ask ourselves, is this a rational function? What do you guys think? Is it a polynomial on top? Yes. Is it a polynomial on bottom? Yeah, it's just x's to whole numbered powers and coefficients added and subtracted. Like that's all we need to be a polynomial. Definitely a polynomial. So what do I care about then? I care about where the denominator is equal to 0. How do I solve something like x cubed minus 4x equals 0? This is like the first section of chapter 13. We did stuff like this, right? Okay, to solve any polynomial, we have to factor it. Is there any factoring we can do with x cubed minus 4x? Can take out a greatest common factor of x. Very good. What's left after I factor the x out? X squared minus 4. Okay, that looks good. Then what do we do?
For the middle x, like where it's just the single x, you like where they cancel each other out. Like instead of a 4 and a 4, make 0.
Oh, you're talking about factoring x squared minus 4.
Yeah.
Is that what you're talking about?
Yeah.
You could do that, sure. So the two numbers that multiply to give you negative 4 and add to give you 0, 2 and negative 2. So you could write that as x minus 2 and x plus 2. You might have also recognized that as just the difference of two squares, that factoring pattern. So now it's factored completely, right? Because everything is linear. What do I do now to solve it? I set each piece, each factor equal to 0. So x equals 0, there's nothing to solve there. That's just an answer. And we can add 2 to both sides to get 2, and subtract 2 from both sides to get negative 2. So we'd say our domain is all real numbers except for negative 2, 0, and 2. Is that okay? But we're going to write that as an interval notation, right? So where does our interval notation start? Same as last time, right? Negative infinity. And it goes up to the first hole in our domain, which occurs at negative 2. And then it'll go from that hole in our domain to the next hole, which is 0. That's correct. And it'll go from that hole in our domain to the next hole, which is 2. And then it'll go from that hole in our domain to the end, which is positive infinity. What do we think so far? This is not too bad, right? We're just doing polynomial things and like piecing it together to make a domain. The way you piece it together is really easy. It's just, negative infinity to the first hole to second hole to third hole, whatever, to the end. So that's good, right? we're not going to worry about ranges for this topic, at least not right now. But we do want to now talk about a major difference about these rational functions. It has not occurred to any of the functions we've talked about. And it's these rational functions can have discontinuities. So what do I mean by discontinuity? If I'm drawing the graph of the function, means for me able to do that, I have to pick up my pencil, that there's going to be a break in my graph somewhere, somehow, where I can't draw it with just like one single stroke of my pencil. Does that feel okay? All right. So there are two types of discontinuities that a rational function can have. We can have a vertical asymptote. So a reminder of what that looks like. A vertical asymptote is like an imaginary vertical line that the graph will approach but never cross. So something like that. Notice to draw that graph in red, I have to pick up my pencil when I get to the vertical asymptote. I can't keep my pencil on the paper and draw that picture, right? That's what we mean by discontinuity. So that's one type. The other type that we can have is called a removable discontinuity. And what does that look like? Well, say we have our graph and it's going along, and then there's like 1 point missing, and then it just continues going along with the same pattern, right? When we draw that missing point, usually we draw an open circle there, like we do for when we drew on the number line, when we drew inequalities, right? So that's like our removable discontinuity. The graph above was like our vertical asymptote. Everybody feel okay visually what we're talking about here when we talk about these two things? Okay. So let's talk about how to find these. And when I talk about how do I to find these things, we're talking about doing this without having to graph it, right? I want to do this just by using the equation of the function, because what we're going to find here pretty quickly is generating a graph for these things by hand is not easy. All right, so let's talk about how to do this. So let's say we have some rational function, p of x divided by q of x. Let's be specific here. So assuming that the fraction p of x divided by q of x cannot be reduced, then the unique real solutions to the denominator set equal to 0 are going to give you the vertical asymptotes. Okay, so suppose you have some p of x over q of x that can be reduced. And when you reduce that, some factor is eliminated completely out of the denominator. We'll call that factor f of x. Any factor that's completely eliminated from the denominator we'll set equal to 0 and solve. The solutions to that will give us a removal discontinuity. And anything left still in the denominator set equal to 0 will give us vertical asymptotes. So this sounds complicated. It's really not so bad. We're going to go through and do a bunch of examples of stuff that can happen to kind of drive this home. All right. So let's say that we have x minus 5 over x squared minus 5x plus 6. So to figure out if we have removal discontinuities or vertical asymptotes, the first thing we have to do is try to reduce this. How do I reduce a fraction? Let's step back and maybe talk about something like this. How do I reduce 4 over 8? Yeah, so I can think about 4 as like 4 times 1 and 8 as like 2 times 4. And then those 4s will cancel out, right? Does that feel about right? What is this process called where I take the 4 and I rewrite it as 1 times 4 and take the 8 and rewrite it as 2 times 4? What do we call that process? That's factoring still. So in order to reduce x minus 5 over x squared minus 5x plus 6, what do we have to do? Factor them, right? Now, the process for factoring a polynomial is different than that for factoring a number, but it's still the same idea. So can I factor x minus 5? No, right? We'd say that's prime, just like if the numerator was like 3 or something. If I had like 3/8, like the 3 is prime, there's nothing you can do with that. How about factoring x squared minus 5x plus 6? Can I factor that? Yeah, how does it factor? You need the two things that multiply to give us 6 and add to give us -5. What are those two numbers? -2 and 3. -6 and 1 will multiply to give us -6, not +6. Easy mistake to make. All right. So we've got this thing factored, right? Now we look to see if we can reduce. Is there anything that I can reduce from the numerator and denominator? I can't reduce the x's because the factors are the parentheses themselves, right? And there's nothing inside a parenthesis that's identical in both the numerator and denominator. So there's no reducing to do. So since that's the case, I can just take the factors in the denominator, set them equal to 0. And I get solutions. Each of those solutions are a vertical asymptote. Everybody's okay with that? So how many vertical asymptotes can I have in a function? Lots, right? As many as I want. Realistically, are you going to have more than like 2 or 3? Probably not. Of course. What if we have something like x plus 3 over x squared minus 9? Again, want to start by seeing if we can reduce. So we have to factor. Can I factor x plus 3? No, man, that's prime. Can I factor x squared minus 9? Yeah, what does that factor to? Excellent. X plus 3 and x minus 3. Can I reduce that? Yes. What can reduce? The x plus 3s. Is that okay? So when I do that, what's left in the numerator? 1. Very good. And then the denominator, x minus 3. So this piece, the x plus 3s are completely reduced, correct? There's no more x plus 3s left. That means it's going to create a removable discontinuity. So I take that piece, set it equal to 0. That'll give me a removable discontinuity. The stuff that's left is going to be my vertical asymptotes. So I set that equal to 0 and solve. And I get a vertical asymptote. Everybody's okay here? All right. Next question is, if I reduce, does that guarantee that I'm going to get a removable discontinuity? No. Let's see an example. So here we have x squared minus 25 over x squared plus 10x plus 25. I want to start by factoring. How does the numerator factor? Excellent. X plus 5, x minus 5. How does the denominator factor? X plus 5 and x plus 5, right?
Yeah.
Positive 5 and positive 5 multiply to give us 25 and add to give us 10. Okay. Is there anything to reduce? Yes, x plus 5s. Are there x plus 5s left? Yes. So even though we reduce that, it doesn't create a removable discontinuity because there's still an x plus 5 left in the denominator. So when I set the reduced denominator equal to 0, that's just going to give me the vertical asymptote of negative 5. Okay, I want to do one more quick example. Does one of these things have to have a removal of discontinuity or a vertical asymptote? Can it just have nothing at all? Sure it could. Let's look at an example. What if we have x over x squared plus 1? I want to start by factoring. Can I factor x? No, that's just the way it is, right? Can I factor x squared plus 1? You can't. It's not a difference of two squares, because it's not x squared minus 1. That we could factor. Here, we have x squared plus 1. There's not two numbers that multiply to give us 1 and add to give us 0. At least not two rational numbers. So there's nothing we can do there. So it is reduced. There's no RD. So if I take this then and set it equal to 0, I'll subtract 1 from both sides, square root both sides. So plus or minus. What's the square root of negative 1? I. Notice that this is not real. That's not a real number. So it can't count as a vertical asymptote because the vertical asymptotes are locations on the x-axis. The imaginary numbers don't lie on the x-axis. They're invisible. So just because we give you a rational function doesn't mean it needs to have a removal of discontinuity. It doesn't mean it has to have a vertical asymptote. It could have neither, and that's okay. What do you guys think so far? It's okay? It's a lot of building on these ideas from polynomials that we've already done. It does get a little tricky here and more complicated as we go, but I'm going to try to go carefully and slowly through this and maybe give you more detail than even is in the notes or the lecture or the lessons that are written out, because I know this is the first time we're doing this. But this is a good stopping point, and this is where we're going to stop. Remember, Tuesday is going to be the test for Chapter 13. We'll pick up 14 later. I think on the asynchronous day next week, I'll have a Delta Math for you guys to work on. Sound okay? All right.